Yo, what's up, folks? So now we start to get into the heavy-duty stuff. I will admit, a little heavy, some heavy-duty coming here, but great physics. Um, this talks about a topic called motional EMF. A lot of you guys that took quote-unquote digital last year um, use the term EMF, and we use EMF, or at least maybe it's just me, but I use EMF and voltage discretely, differently. And for EMF, that stands for what we call electromotive force. I use it in this context of motional EMF that we can, well, we'll sort of get to it. But here's the deal. If we were to try to fill in these blanks, what we can say for charges that move, well, it doesn't even have to be charges that move, but as long as there's relative motion between charges and magnetic fields, then force will be applied to the charge. Now, what that means is in some cases we can make that charge orient along the direction of a wire. And that can make current. And so we call this motional EMF. Right? We don't need a battery to provide electrical energy. We can do what we call induce an electromotive force by moving a wire through a magnetic field. Or we could move the magnetic field near a wire. Okay, those things produce, or can induce, really, electromotive forces or potential differences, and therefore currents. All right, so if we look at a case like this, let's take this wire and move it like that. We move it across there. All right, well, we should be able to tell that if we look at an individual charge that's in the wire that's moving this way, there's velocity. We can use our right-hand rule to say, okay, let's see, this thing, it's going right, my right thumb is right, the field is in, my fingers are in. That means the force on this thing would be upward. All right, that means you would end up with, this thing could make current in that wire that goes upward. There's an induced current, we say, upward, which means that this is really like, this thing now has an induced EMF, or a potential difference, where there's a certain potential here, a certain potential there, and there's a difference in those potentials. Therefore, just like if there was a battery connected with terminals like you see, a positive here and a negative here, we'd get a current upward. All right, but we don't need a battery. We just need to move the wire, or move the field, all right? Move the magnet. Now, there's a bunch of cases in which, current's not actually going to flow in that wire, all right? Because current flows in closed circuits. But if we take loops of wire, like you see in these other 4 examples, forget about that. If we look at a closed loop like this, if we were to take this loop of wire and move it like that, across the field like that, well, what you can do is look at, a charge here and a charge here. Positive charges in each place. They're both moving this way. At the instant when this thing is moving through the field, there's B. The field's into the page. Well, both of those charges would feel a force upward. Well, if both charges are pushed upward, neither of them's going to go anywhere, because you can't jam the charges together in some place. You'll get no current in a place like this, or in a situation like this, because both charges are pushed the same way. So in this case, we say this does not induce an EMF. EMF. And again, EMF is the same thing as voltage for our non-digital peeps. Now, what if we look at a case like this where somehow magically this loop gets bigger? This loop gets bigger. Well, let's look at a charge over here. That charge moved this way. The charge over here moved that way. we know that the charge that moves to the right gets pushed upward. The charge that moves left, we put we put our right thumb to the left. We put our fingers into the page. This one's pushed like that. This one actually does induce a current that looks like that. I induced. I'm not trying to use I and E interchangeably here, but if charges are pushed down here and up here, well, hopefully it makes sense. We could get a current in this loop that goes around counterclockwise like that. Yeah. So this one does do what we call induce an EMF. The only way for there to be current is if there's a potential difference, right? And that's what EMF is. Now, a case like this, we only move one wire. Well, just like we've been saying, charges in this wire, the only one that's moving, are going that way. Charges pushed up like that. So this thing is going to induce a current that goes like that. I induced. And again, the only way for there to be a current is if there's an EMF. So this does induce an EMF. Okay? This one, sort of weird. The loop's in the plane of the magnetic field. So, the charges, this one does something real weird. See if you can tell me what happens to this one. You can tell me what happens there. Something real interesting happens to that one. Okay? Okay, now, let's talk about what quantity actually changes in this situation. This situation being the one where we slide. This is a super, super common AP Part 2 question. It'll say something like a metal rod is slid across two conductive rails. A lot of the time you'll have a resistor here. We'll see those in a few minutes, ones with the resistors there, or in a few slides. All right, blah, blah, blah. This is a very common case. So we're going to talk about why is there an EMF induced? Well, we can explain that with our right-hand rule thing. How much of a EMF is induced, we'll explain a couple of ways, and here's one of them. All right. Well, when's there any induced EMF? Well, yeah, blah, blah, blah. Here's what we really want to talk about. What quantity actually changes? Well, if we go back to the beginning, when the wire was here, we had lots of magnetic field poking through an enclosed area, right? So we had this as our enclosed area. I'll call that A initial, right? And then we have, later on, we have this. I'll call that A final, the enclosed area final. So there's a change in area of that enclosed or that closed loop. Okay? And so what we're going to define is this quantity called magnetic flux. And we use a phi for magnetic flux. By definition, magnetic flux is magnetic field times enclosed area. Believe it or not, it's one of these. It's a B dot A. Okay? And so, well, in the beginning, we had a certain B, right? The same B. B is what it is. There's just some value of B. And we had some initial, area. That gives us some initial flux. Well, later on, we had a different area, and therefore a different flux. Well, we say that when is there an induced EMF? When we call it magnetic. You don't always say magnetic. You can if you want. When flux changes. All right? And is this the same thing as sort of saying, well, when this rail slides and there's a charge in here that's moved to the right? Yeah, sort of. Same thing. I mean, it ends up, you can explain it both ways. But we say, here's the big deal. This is what's called, well, I'll wait for the next page for that. Okay, but when is there an induced EMF? Bottom line, when flux changes. And we might even want to say this in a closed, look at that, loop. parentheses. So if we want to induce a lot of EMF, well, we can do this. We can, well, here's what I will say. Change flux fast. All right, just like our F is QVB, where the faster we move the thing, the bigger the force. Well, the bigger the force, the faster you'd get a current to go. So that means for the biggest possible EMF, change the flux as fast as you can. Okay? So induced EMF, there's an equation for it. It says that EMF induced is change in phi over change in t, or just t. Okay? Now, phi can change in one of really three ways, but right now you might be able to see a couple of ways. How can we change flux? We can either change the strength of the field, or we could change the enclosed area. We actually don't have to change the enclosed area. We could take the field from this strength, to nothing. Somehow the field is decreased. Well, that would change the flux, and that would create an induced EMF. It doesn't matter how you change the flux, as long as it changes, a potential difference, an electromotive force, an EMF, is induced. Okay? Click. There's an experiment that I gotta show you, called Faraday's experiment. I think it's Michael Faraday, British dude. He did this. He took a battery with a switch there. You know what I want to do? I'm going to show you this. You gotta have me show you this. All right, I'm going to talk about a few cases. All right, now some more about flux. All right, let's look at a loop of wire. All right, in a magnetic field that looks like so. And we're going to look at that loop in a few different orientations. Okay, the question is flux the same everywhere? There's the same magnetic field. There's the same area of that circular loop. But there is a difference in flux in each case. Here, we get the most flux. Here we get medium amount of flux. Here we get, actually, no flux. None. All right? And what you heard me say a while ago at one point was, in order for QVB to be the biggest, we want V to cut across the most magnetic field lines it can. Well, for flux, what we want for the most flux, like we saw on this page, there's lots of flux here because the field cuts through the loop, goes right through the loop. All right, so sorry, in this case, or in these cases, notice that in the top case, if we look at, well, this is literally what we call the area vector. That's a vector that we call the area vector. We say that the area vector is quote-unquote normal to the loop. Normal means perpendicular. Right? Like a normal force is perpendicular to the surface. Right? So that vector there, A, we sort of pretend like the loop is like a, I don't know, you have a sheet over the loop and then you poke a pin through that, and that vector A is always perpendicular to the surface of that loop. Okay? In that case, there's no flux. In this case, there's our area vector, we get some. In this case, here's our area vector, we get a ton. The most possible flux. All right, so that means that the flux equation really must include something else, where if this angle right here between B and A is 90, then we get, well, flux is 0. If this angle here is, I don't know, 45, well, we get a certain amount of flux. If this angle here is, well, it's supposed to be 0. We say that this angle between those two things, so here this angle is 0, we get the most possible flux. That means that the real flux equation has to include cosine, right? Cosines are big when angles are 0. They're nothing when angles are 90. So you saw me write a while ago that flux is B dot A, which really means B parallel with A. And the way we do that is we do B A cosine theta, where theta is the angle between B and A. Now, one thing I didn't mention is the units of flux. The units of flux are called Webers. They're called Webers. And a Weber, apparently, is a Tesla meter squared. Both of those, obviously, are okay to write for flux. Okay? Okay. Oh, yeah. Oh, poop. Yeah. So here's the dealio. Right now, lots of flux. Yes? Lots of flux. But if we want to get EMF, and therefore current, let me move this stuff, folks. I'll rewrite up here. So flux is B A cos theta. Right? So lots of flux here, tons of flux. But by itself, lots of flux doesn't do anything. If we want to induce an EMF, we need to change the flux. So what we can do, if we wanted to change flux, is we can do that. All right? Right now there's none, there's lots, there's little less, there's none. There's some, there's lots, there's some, there's none. There's some, there's tons, there's some, there's nothing. All right? So if that flux keeps changing, what we get is an induced EMF, and therefore an induced current. All right? So this idea of rotating loops of current in a magnetic field is a hugely, hugely practical application for making current. Okay? Okay. This might be my crowning achievement in terms of PowerPoint-based animations. So this Faraday's law, and Faraday's law is, just so we're sure, Faraday's law is that induced EMF is change in phi over change in t. Hey, what happened? Back it up. Good. What? No. Yes, fine. So here's what Faraday's law says. Faraday's law says if flux changes over time, you can induce a current. All right? So we get this loop of the solenoid, really, and we take a bar magnet, and the bar magnet's magnetic field looks like that. Well, if we move this magnet, right, we talked about moving the loops or moving the wires. Now this shows us that if we move this magnet, yeah. Well, as we move this magnet, what you'll notice, or what you should have noticed if this stupid animation worked. Here I am touting my animation skills, and there's no animation. If this magnet moves left, more magnetic field lines would cut through that area vector, or that area A. What's your problem? Why won't you behave? Sure. Now this causes an induced EMF. And the magnitude of that induced EMF is, well, delta phi over t, however much the flux changes, and however long it takes. Right? If we bring the coil to the right, well, the same things, but except the only difference would be fewer magnetic field lines would cut through A. I'm putting that A there just to sort of say it's kind of like that area there. Okay? Really, well, I guess this area here is supposed to be just like the area enclosed by these loops of wire. Okay? That would also cause an induced EMF, and therefore a current, and therefore a current. And the magnitude of that would be, well, delta phi over t also. All right, so I think the big point of this is to show you that you can move magnets instead of moving loops of wire and still induce current or EMF. Okay? Okay, now, another way to figure out induced EMF. We know one thing, right? So method 1, induced EMF is the delta phi over delta t, or the change in the product BA cosine theta divided by delta t. Method 2 says, let's slide this bad boy across here. And, well, as we do that, yeah, now, the charge that moves from one end to another, from here to here, moves through a potential difference. All right? And that potential difference is equal to the amount of work required per unit charge to move it from, well, let's call it this length L, to move it that length L. Okay? So this is really, hang on, I just want to see how much space, I have to work in. Good. So we say that V is work per unit charge. That really means that EMF is work per unit charge. Well, the work is force times distance, right? So I'm going to call that F times L over Q. Well, the force, we know, this is a moving charge, a charge that was moving this way at a velocity V, and a magnetic field B, right, B. So that means that the force is QVB. There's our times L over Q. There's our over Q. Well, these charges just drop away, and we have an expression for EMF. Another one. It's Q. No, it's not Q, stupid. It's V. B. L. Okay? Those are two different methods to find induced EMF. And we can show you that they're the same thing if you really want to see it, and who doesn't. So if we say, let's see, E is V, V, L. Well, V is, I don't know, that thing went this distance, let's call it X. The bar did. So we can say that V is X over T times BL. Ooh, and look, X times L is the change in area. That's how much the area changed. All right, so this turns into, well, delta A times B over T. Now, the theta here, right, theta is actually 0. So we just say that the cosine part of this is 1, and we don't need it in there. All right, so these two expressions give you the same thing. But these are the two you need to know for sure. BBL, delta phi over delta T. Okay? Here's the quintessential part 2 problem. We'll get to that, I think, together. Oh, that's good stuff, back EMF. Good, good. So I think that's good for today. Okay, folks? Yeah, that's good. I like it. Good physics. See you soon, guys.